Good afternoon, everybody. I have a great privilege and pleasure to introduce our second keynote, Frank Harrell. So we weren't really sure if we need to introduce Frank at all, or everyone will be familiar with our guest. But let's at least try. So why Frank Harrell? He's a researcher, so here you can see an impressive Google Scholar profile with more than 80,000 citations accumulated over his research times. You can see Frank Harrell as a lecturer, and here also I want to plug in his course, a free web course in a good introduction into biostatistics. So please refer to the site biostat.org/BPR. Frank is a really passionate teacher. I'm sure we all know this. We all know this, and he's so grateful that he's sharing his teaching materials for free. So if you are looking for an opportunity to improve yourself, that's definitely a chance. But first and foremost, we want Frank here because Frank is an R user. He was S user since 1991. He was then converted to R back by amazing Bill Venabos. Frank is maintainer of important R packages. So there's, of course, RMS. And I suppose everyone knows RMS book also. The RMSB package might be a bit less well known, but it's the Bayesian methods for RMS. And package HMISC, which was, at least for me, HMISC was kind of our discovery, because when I discovered functions converting outputs to LaTeX or converting or the describe function from the HMISC package, I really found out that working with R could be much more easier than I was expecting. And of course, Frank is very active. He was participating in the R help mailing list from the very beginning. He's very often a guest on Stack Exchange, and he is very easy to talk to on Twitter when he's also posting his important series of statistical thoughts of the day. And last but not least, Frank Harrell is one of us. He was active where the data science as a buzzword wasn't really a thing, but he was always very much connected to the field itself. So here I put it, two of thoughts of Frank Harrell that can be found in the Fortune package on CRAN. So first touches the topic of connecting statistics and programming, which was a heresy for many back then. And the second touches an important topic of knowing what we are doing during the data analysis, and that's actually a topic of today's lecture. Frank will tell us which mistakes we are frequently, which mistakes frequently affect our data analysis, and how, and we will, and I suppose that after this talk, we'll be a bit more sensitive, a bit more cautious about what we are doing when we are analyzing our data. So I'm stopping my share screen. Frank, the floor is yours. Good luck.
Michael, I really appreciate the kind introduction, and I'm going to find my screen to share, and I hope it's up now and you can see it okay. So Michael, it's a great honor.
It's visible.
Great, thank you. It's a great honor to be here, Michael. I appreciate very much the invitation to speak today. And I'll be talking about various controversies in statistical analysis, and much of this will involve predictive modeling, which is a very big topic nowadays. So let's get right into it. So this is already very controversial, that external validation is overrated. So why would anybody say something as crazy as that? there are people that are taking a stream of data and splitting it into two parts and calling that external validation, which is not external validation. But there's uncertainty about what we mean by external. Many people take external to mean in another time or another place. And if you're really trying to show that your predictive model works in another country or another region or another time, it's much better to model time and region in your model than it is to be surprised. So what happens is people are surprised, and then they view the model as failing to work because it did not validate in Germany when it was developed in Poland. And so that's really not a lack of validation of the model. Usually that just means there are regional or country differences that should have been modeled. Similarly with time trends, you can find that a predictive model may work in earlier years and not in later years. And it is a mistake to call that a lack of validation. That's just a time trend that is easy to put in the model. So you need to learn about geographical and health system differences and learn how to get predictions for other times and places that were not in your data set and trying to model that as best as you can. Another issue with external validation, and we're talking in a general sense now, whether you're using statistical models or neural networks, random forest, it doesn't really matter. What does external validation do? Well, it validates a model if it is the model. So what does that mean? Well, the model might mean a model that you fully specified, including all the variables, and the only thing that you did was to estimate their weights. And so you're estimating things like regression coefficients. So when you fully pre-specify a model, external validation is validating that model. But when you use feature selection, things are not what they seem. And what you're really doing is validating an example model. So when you do feature selection, you find that the features are essentially a random sample of features. Feature selection is not reliable in most uses. And so it's a process of selecting features that's highly unstable. And so you're actually seeing whether the model that you developed using feature selection validates, you're validating an example model. Whereas if you use resampling, you're validating a process. And I think when you're doing feature selection, it's really important not to validate a single example model, but it's better to validate the process you're using. And that will be honest about instability of model selection. So resampling will repeat the process and it will find different features every time you have a sample with a resample, such as in the bootstrap or with cross-validation. This is another controversial point, and there's a long history here that I don't have time to go into, but we have had several scandals in biomedical research. They often involve biomarkers, and they often involve cancer research. And we're finding that a lot of people are doing research who are not really qualified to do high dimensional research. And many of the failures that we're seeing of research findings to replicate are just entirely predictable from a statistician standpoint. The quality of the research and the analysis methodology that you use highly influences the reliability and usefulness of the resulting research. And so you may find that there is more benefit to validating researchers than there is to validating their models. And it is much easier to validate their analyses. And so by validating someone's analysis, I mean that, first of all, can you get an exact replication of what they obtain of their data? So if you use the same statistical method and use the same data, can you get the same answer? It's shocking how often that is not the case. So there was a famous scandal at Duke University in North Carolina in the US where investigator Anil Poti claimed to have a wonderful biomarker signal for telling which type of lung cancer is sensitive to which chemotherapy. So it would be a nice thing if it were true. And it turned out to be completely false. And the investigator Pody and his team and his mentor, Nevins, they used really irresponsible research and made every mistake you can make, including having the genes off by one gene in an Excel spreadsheet where they moved one column over. They had the chemotherapy sensitive and the chemotherapy resistant tumors exchanged. So they were actually predicting chemotherapy resistant when they thought they were predicting chemotherapy sensitive. So everything that could go wrong went wrong because they did not engage in reproducible research and they didn't have good lab practices. And so people tried to get their data to try to replicate their results and they refused to share the data. So that's usually a signal that something is wrong. Lisa McShane, a great statistician at the US National Cancer Institute, that's the institute that was giving them the money to do the research. So they had a lot of power to ask for data. She asked for data and could not even replicate what the researchers got by using their program and their data. If you ran the program in the morning and you ran it in the afternoon, you get completely different answers. There was no signal in the data and there was a randomization process. So there was pure noise in what was found. So once the data were shared, it became very obvious. And an independent research team can quickly check reproducibility, and they can check the specificity of the statistical analysis plan, and they can also use their own statistical analysis plan to reanalyze the data to check for the robustness of the results. A good number of scandals that have happened in biomedical research could have been prevented if the original researchers had an independent team replicating what they were doing. Now we get into a totally different area, which is Bayesian modeling. And Bayesian modeling is really catching on, and I'm very thrilled by this because it solves a lot of problems that we have not been able to solve with traditional statistics and frequentist methods. So one of the problems is we like to use penalized maximum likelihood estimation. We like lasso, elastic net, ridge regression. Those are all special cases of penalized maximum likelihood estimation. And those methods can work well for prediction, but they lack inferential methods because confidence intervals and p-values were created for the case where you're not biasing the results towards zero, which is what you do with penalized estimation. And so we don't really have our statistical tools ready for us for p-values and confidence intervals when you have done shrinkage or penalization. But with Bayes, when you use shrinkage priors, say a shrinkage prior for ridge regression is just a normal distribution with a mean of zero. A shrinkage prior for lasso is a double exponential or Laplace distribution that has a spike at zero. Once you use a prior in Bayesian, you get posterior inference that's just the same as posterior inference using a flat prior. So you have all of the inferential tools are used without any modification once you go to Bayes, and that's not really available in traditional statistics. You can also use special priors, such as the horseshoe prior, that work better than lasso or elastic net. And you can choose your priors to match biological knowledge, whereas what we tend to do with like the GeoLim net package in R is a wonderful package that's super fast. But we tend to use methods because they're fast and we don't stop and think, well, what is the population of effects? If you had a genome-wide association study and you looked at 1 million SNPs, what do we think the population of log odds ratio should be from 1 million features? Well, you can envision that population and encode it as a prior in the Bayesian world. And we're not choosing the method because the software is fast. Now, can you handle ordinal predictors? This is a key challenge with traditional statistical models. These are categorical predictors where you want to assume monotonicity. And it's actually very hard to do that in the frequentist traditional modeling setting and very easy to do in the Bayesian setting. And then in the Bayesian setting, your degrees of freedom for nonlinear effects can be data determined and still preserve the Bayesian operating characteristics. Whereas in the frequentist world, we have trouble when we don't set the number of parameters as a constant in the model. We have other advantages of Bayesian modeling. I think once you get into Bayesian modeling, you see that it's much more unified. For example, you might not need a separate imputation step and then a modeling step. You might be able to do it in a single unified Bayesian model. So you do joint modeling of the missingness of your variables and the modeling of the outcomes. And by doing this joint modeling, you don't do any imputation. And that is a much more streamlined way of thinking about it. Validation is less necessary because in the Bayesian world, overfitting in the usual sense of the word does not occur. What occurs is disagreements between an analyst who used a flat prior and the reader who wanted to use a shrinkage prior for the regression coefficients. That disagreement will be seen as the model giving predictions that are too variable, they're too extreme, compared to somebody who wanted to use a horseshoe or normal skeptical prior for the betas. So you translate the problem of overfitting to the problem of selecting the priors. And then you have all the usual advantages of Bayes, such as calculating direct probabilities. So you don't say what's the probability of getting data more extreme if the effect is 0. You say what's the probability the effect is greater than 0. So you can compute things like what's the probability that a nonlinear curve is monotonic? What's the probability that the blood pressure reduction is more than 5 millimeters of mercury? You can compute all of these probabilities with Bayes very easily. So it's not the indirect p-value approach that we're used to seeing in traditional models. And then I want to spend time on the mirage of variable selection. This is something that people are not stopping to think enough about. And so one thing they're not thinking enough about is the idea that parsimony is the enemy of predictive discrimination. So if you want to have the best predictive discrimination, you don't want to spend any of the data trying to figure out which features to use. Anytime you try to select features, you're actually using some of the information in the data. And in my course, my RMS course, I show the Maxwell's demon analogy, where this demon is stealing information in a thermodynamics experiment. And this involves the first law of thermodynamics and the preservation of entropy, or entropy must increase. And so it's a really similar thing in feature selection, that you're actually stealing information from the system in order to make judgments about which features to keep. And it makes your discrimination ability go down in most cases. And the problem with variable selection or feature selection, the real problem, the simplest way to say it, is the probability of selecting the right variables is 0. So there's no chance that you can use data to tell you which elements of the data to use. And so it's a basic information limitation, that you don't have enough information unless you have millions and millions of observations and not too many candidate predictors, that you have the information basis to do feature selection. People are not thinking this through. So you'll see a lot of papers calculate the false discovery rate, and they don't worry about the false negative rate. And so what does that mean? Well, they're trying to control the fraction of the time that that variables are declared important, but they're not caring about the false negatives, which is the features that are not selected or assumed to not be important. But if the false negative rate is high, you have no ability to say that the features that were not selected are not important. And so what you find is the fraction of unimportant features that are not selected is much greater than 0, and the fraction of important features that are not selected is high, so that's bad. The fraction of unimportant features that are selected is also high, and that's bad. So you have both of these things going on, and this is not very satisfying. And this is why it's very uncommon for people to do feature selection and somebody to replicate that with another data set and find the same features. They almost never do, because they're asking for an answer to an impossible question. If you do a confidence interval for variable importance, you'll really expose the difficulty of the task. And I really recommend that people do this much more often. And it's very easy to do with the Bootstrap. All you have to do with the Bootstrap is to do a few hundred resamples of your data and repeat your whole analysis every time from zero. So you start over with your feature selection and you start over with your coefficient estimation. And so with the Bootstrap, you can calculate confidence intervals for things we're not used to seeing confidence intervals on. So here's an example that shows how difficult it is to select features in a very trivial example. So this is an example where we had 12 candidate features, only 12. The coefficient of the ith feature is I. And so the beta coefficients are going to be 1, 2, 3, up to 12. And so you already know that the 12th variable is the most important and the first variable is the least important. The residual standard deviation is 9. And with 300 sample size on only 12 continuous predictors, and the dependent variable is your highest information dependent variable, which is a continuous variable, normally distributed, conditional normally distributed. The residual standard deviation is not that large. We're going to rank the partial chi-squares, which is the same as ranking the partial r-squares. So any measure that you want to take as your variable importance measure, you can insert here. It doesn't matter which one. And so what happens when you repeat your process of feature selection? I'm sorry, in this case, we're not actually doing feature selection, but we're calculating the variable importance measures that might allow you to do feature selection. And what do you get from that? Well, the variable that is the least important in the population is x of 1. It should have come out here with a rank of 1. And in our sample of 300 subjects, it came out as the second weakest variable. Variable 12 should have come out as the strongest variable here at a rank of 12 in terms of the rank of the variable importance. Here was partial chi-square or partial r-squared. And the observed importance of the 12th variable was number 9. So it came out as the 1, 2, 3, 4th strongest variable, when in the population it is the strongest variable. Now, our 95% confidence interval for the rank of the variable is from 7 to 12. So this confidence interval 7 to 12, it does contain the true value of 12. And the confidence interval from 1 to 7 does contain the true value of 1. So at least the confidence intervals are telling us that we're not off in that regard. But the thing to look at is how wide the intervals are. So what do we know? This variable would be called, let's see, the variable that came in the weakest was x of 3. It should have been x of 1. So x of 3, the data are consistent with it being the weakest all the way to the 7th weakest. So all we can say, the variable that came out the weakest is not in the top 1, 2, 3, 4, 5. So it's not in the top 5 out of 12 features. So the knowledge that we've gained about the ability to say that x sub 3 is a loser is very limited knowledge. And so our confidence interval says with 95% confidence, loosely speaking, the rank of this variable is weakest to the 7th weakest, but that is a very wide confidence interval. Now think about how easy this task is. We have 12 candidate predictors and only 12. We have a good sample size for a continuous outcome variable. So our signal to noise ratio is good. And yet we still have great uncertainty into saying what is the importance of the variables. And so once you get into highly collinear predictors and you get into hundreds of features, these confidence intervals just get wider and wider and wider. So the Bootstrap confidence interval will expose the difficulty of the task, and it will really show why feature selection fails. The data do not have the information necessary in most cases to do reliable feature selection. If all you care about is prediction, it's better to not do feature selection. Here's an example using the lasso where we have 500 subjects and we have 500 candidate features. Our y variable is binary with a probability of 0.5 of equaling a 1. All of the x's are binary with a prevalence of 0.1. and we're doing 2,000 simulations. And we're going to do cross-validation on the deviance to select the lasso penalty parameter lambda. Now, to give lasso the maximum chance, we're going to sample the beta coefficients from a Laplace distribution. That's exactly what is optimal for the lasso. So we're giving it every chance. So that's our double exponential distribution. It has a sharp peak at a beta equal to 0. And we're going to scale the betas equally such that the overall true linear predictor, after you have sampled the betas from some population of betas, the overall true linear predictor is a C index of 0.8, which is your area under the receiver operating characteristic curve. So this is a typical model with an AUROC of 0.8. For each true beta, compute the fraction of the 2,000 simulations in which that variable was selected by the lasso. And this is a kind of plot we don't see often enough, but I think it sheds a lot of light, just like the variable importance confidence intervals would. So this is our real regression coefficient that we simulated from. And we have a concentration of these around 0, which is what the Laplace distribution would say. And then we have some very powerful negative effects and some powerful positive effects for our regression coefficients. This is the probability that a variable is selected by the lasso. So what do you want this probability to be? Well, in a very small neighborhood of 0, you want the probability that lasso will select the variable to be 0. So that would mean that lasso is properly telling you that if a variable is weak, we will not select it. What happened instead? We see that the lowest probability of selection, even for a true 0, was about 0.1. And if you look at the average probability of selection for something that's a true 0, it's a little bit higher than 0.1. And so it goes up to maybe 0.15, something like that. And so we failed the test of being able to exclude the truly irrelevant weak variables. Now, what do we want this graph to look like with regard to everything else? Well, if you're outside of this small zone around 0, you want the probability to be at 1. So you would like to know that the lasso has a very high probability of selecting strong variables that are truly strong. What do we see instead? Well, it was never close to 1. The highest probability of selection was about 0.7, let's say 0.78. So even variables that are truly really strong over the 2,000 simulations, here's a variable that has a true beta greater than 1, the probability of selecting that variable by lasso is only about let's say a little over 0.8. So not only is this not close enough to 0, this is not close enough to 1, and you have a lot of variables that are the hardest ones to make a decision on. These are intermediate variables, and you see that our probability of selection is in the gray zone close to 0.5. So this is far from, you want this to be a 1, and then you want this to shift dramatically to 0, and then you want to go back up to 1. What we see is really far from that. So what is the currently most stable model selection method? That's assuming you actually need model selection, which is questionable. The gold standard is a full flexible Bayesian model with carefully chosen shrinkage priors that are not necessarily sparsity priors. And then using a method of Peronin and Vitari, they have a way of projecting that full model onto simpler models if you need that. So they have this method called projection predictive variable selection, and they have some very nice resources on the web, including this R Markdown notebook that goes through a very nice body fat analysis. So I very much encourage you to look at that notebook for their analysis. Then we get into machine learning versus statistical models. How do we choose which method we're going to use? Well, the first thing we need to know is what are some definitions? Because if we don't have definitions, we can't really talk to each other, and people will not know what we're doing. And so what is a statistical model? It's something that has a probability distribution for the data. It's something that favors additivity in the vast majority of cases. So we have things like beta 1x1 plus beta 2x2. It has identified parameters of interest. It gives you inference, estimation, and prediction. And statistical models are most useful when uncertainty is high. What is machine learning and how does that differ from statistical models? Well, machine learning is algorithmic. It gives equal opportunity for interactions as for main effects. It's useful for prediction, and it's most useful when the signal to noise ratio is high, which occurs when you're doing visual pattern recognition, self-driving cars, language translation, sound recognition, and so on. Deep learning, which is exactly the same thing as neural network, is just rebranded for advertisement. Deep learning is an example of machine learning. And another example would be random forest. So an example of statistical model would be Lasso, because Lasso is fully additive. It has identified parameters. It is useful for estimation and prediction, not always directly for inference, but it has been adapted to that. And it assumes a probability distribution for data. So a lasso is a highly parametric statistical model versus random forest or neural networks. And Norm Matloff has a nice white paper showing that neural networks are essentially polynomial regression. And there's a talk I have that goes into more detail about that. Another thing that's important is selecting measures of predictive accuracy. And so what are the gold standards of predictive accuracy? There's many gold standards, and unfortunately, the gold standards, which have been around a long time, are not the ones people are using. So one of the gold standards is a smooth, flexible calibration curve. And in the frequentist world, a gold standard is the log likelihood that you can achieve with the model. In the Bayesian world, that would be the log likelihood plus the log of the prior. And another measure that's very general and has great statistical properties is measures of explained outcome heterogeneity. And one of the ways to look at that, which is in ordinary linear models, is related to is just the sum of squares regression, which is the numerator of R squared, is to look at the heterogeneity of the prediction. So a model that has a high variance of the predicted values, y hat, is a model that's going to be valuable. It has predictive discrimination. You don't want to give the same prediction for multiple subjects. And so measuring the variance of the predicted values is a key to understanding discrimination of a model. Relative explained variation, such as relative R squared or relative variance, is an excellent way to compare two models. And I have this blog article, fharrell.com/post/add value, that goes through this in more detail and gives a detailed example. So relative explained variation might be to get the variance of y hat from a full model and then compare that to the variance of y hat from a submodel, a reduced model, and see how much this variance goes down. That would be a loss of predictive discrimination. And that does assume your model is somewhat calibrated. So the majority of machine learning papers do not demonstrate adequate understanding of predictive uncertainty. And there was a recent survey of machine learning used in medicine that showed that less than 1/10 of the papers included a calibration curve. This is a scandal. This is a Trump-like scandal to have a paper that claims to have predictive accuracy and to not include a calibration curve is probably about the worst mistake you can make. Proportion classified correctly is still used, even though we know this is an improper scoring rule. It's easy to trick a rule like that. It's very insensitive, and it will tell you the wrong answer and select the wrong model. So proportion classified correctly, along with sensitivity, specificity, precision, and recall, these are all discontinuous measures that will be optimized by a bogus model, a model that is known to be wrong. ROC curves are highly problematic. The coordinate of an ROC curve is sensitivity and 1 minus specificity. These are improper scores that have transposed conditionals. And so when you have transposed conditionals, you're conditioning on the wrong thing. In this case, you're conditioning on the future to predict the past. So that's a transposed conditional, or you're conditioning on the unknown to predict the known. So every coordinate on an ROC curve is a conditional probability of the known, which is like biomarker greater than some cutoff, given the unknown, which would be disease status. And so that transpose conditional makes the ROC curve misleading. And it makes it only apply to retrospective studies like case control studies where the sampling is transposed. It also invites dichotomization of predictors, which is a terrible idea and it's not insightful. And I've seen probably 10,000 ROC curves in the last 20 years, and I've never seen one, not a single one, where there was insight provided by the ROC curve. It has a very high ink to information ratio. So we need to use measures that relate to decision making. So the optimum Bayes decision is one that maximizes expected utility. And what is expected utility? Well, it is a convolution of a utility function and the posterior distribution that describes what we know about parameters in the model. So the expected utility uses the posterior distribution of the outcome probability for a patient or a subject combined with the consequences of the possible wrong decisions. Those consequences are measured by a loss, utility, or cost function. It doesn't matter what you call it. Measures that have transposed conditionals, such as sensitivity and ROC curves, and also the ROC curve area or concordance probability, C-index, these do not enter into the expected utility in any way, shape, or form. The expected utility, these are completely irrelevant for that calculation. So what does enter into the expected utility is the posterior distribution along with the utility function. And so we need to be using methods that are consistent with expected utility, even if we don't have a utility function. So what is consistent with that is the posterior distribution, which is going to be telling you your uncertainty around, say, your predicted risk of an individual patient having disease. So I think you can't have a full understanding of how to judge a predictive model or a machine learning algorithm without understanding decision theory. And once you understand decision theory, you'll see what are the inputs to optimum decisions that minimize bad consequences and do so with certain probability. And then you'll know how to judge your model. Relative explained variation is the ratio of variances, and you can compute something called an adequacy index. You can make various scatter plots, and I'm just going to show very quickly an example. This is a diagnostic model in medicine where we're diagnosing coronary artery disease, and we're given patients age, sex, and cholesterol, and we're counting cholesterol as the new test. So you get a logistic model for predicting the probability of disease without knowing cholesterol. So this is called the pretest model. And here we have the probability of coronary artery disease. These are estimated probabilities along this axis from our binary logistic model. And you see this distribution. Now, when you plot a distribution of predicted risk, this is one of the most important graphs you can make. And this is a graph we almost never see in the machine learning world. And so this distribution, if there is just a single bar at 0.5, your model is not worth anything. If your distribution puts a lot of people in the very high probability range and a lot of people in the very low probability range, that's very good. So this is the distribution of predicted risk if you do not make use of the cholesterol variable, so that we call that our new test, like a genotype. And we have a variance of the predicted risk of 0.047. Now, if you added cholesterol to the model, and we have to interact cholesterol with age, and cholesterol has a nonlinear effect, that's all handled in the model, you see that this distribution changes. And the biggest change is instead of this big group here at a probability around 0.3, we're now moving more risks lower in this tail. So we have now created more patients that we can be estimating they have a low risk of coronary artery disease. We didn't really change so much in the high risk over here, but we added more patients to the lower risk interval. So comparing this distribution to that one shows you the relative utility. And if you just calculate the variance of these numbers going across, you see that that variance is 0.057. If you took the ratio of that to that, 0.047 over 0.057, you have the relative worth of the smaller model with in relationship to the bigger model. This is another graph for showing that sort of thing. This is the predicted risk from the pretest model that just has age and sex in it. This is the post-test probability. This has cholesterol in the model, interacting and nonlinear. So you can see that if you started out at a point of uncertainty, your probability of disease is 0.5. Without knowing cholesterol, you have 0.5. What happens if you know cholesterol? Well, you see all these dots, and you can summarize that with quantile regression. So this is the 25th percentile of the post-test probability given the pretest probability is 0.5. And this is the 75th percentile of the post-test probability. So this is the interquartile range of the post-test probability when the pretest probability is 0.5. So you see we're typically moving patients to about a 0.35 to about a 0.7 who started with a pretest probability of 0.5 when you don't know their cholesterol. I think this is a great way to summarize the added value of the cholesterol variable, or anytime you have a smaller model that you're comparing to a bigger model. And you can also compare it this way and look at it with in relationship to a specific variable. What is the difference between the pre and post-test probability, and how does that difference relate to the age of the patient? So you can see that patients that are older, knowing the cholesterol doesn't tell you much of anything. What it tells you is when you're younger. So if you're in this age range over here and you know your cholesterol, your pretest probabilities will tend to be more different from your post-test probabilities. And this is showing quantile regression smoother on that. But if you just look at the dots, you'll see how the post-test and pretest are more different from zero and more systematically as you get into the younger age group. So you can look at the yield of the new variables as a function of another variable like age. So that's the end of the presentation, and I hope I've presented enough things that are controversial to people and that they will feel free to ask questions and bring up discussions. I want to thank the group for listening, and thank you again, Michael, for inviting me.
Thank you, Frank. Would you mind moving, stopping sharing your screen? Because this way will be both visible at the same time.
Yes.
So I must admit, yes, that was definitely one of this maybe not bridge burning talks when you are definitely showing that you are no longer associated with some discipline, but definitely full of jobs and actually very important tips that I can see. So first and foremost, we have a question from audience from Muhammad. So, in what extent do you think the directed acyclic graphs can help us choosing the right variables for inferential Bayesian statistics?
I think it's a big help whether you're doing Bayesian statistics or frequentist statistics. I have a colleague in California, Drew Levy, who has a beautiful handout about this, and he always takes part in my Regression Modeling Strategies course when I teach the 4-day course each May to show the importance of DAGs in choosing a model. It's really important to respect the causal pathways and to not have collider variables and that sort of thing. I would say it's very important, and this is where people doing machine learning on large numbers of variables are failing the test, because we're seeing papers published in machine learning where they used 11,000 variables from the electronic health record and did not even take note of which variables were independent variables and which variables were dependent variables. So that's like the worst violation of a DAG that you could have. So I think DAGs are very important.
Would you recommend using DAGs even for very with data sets with many features? Because then they get really complicated.
Yeah, I don't think, I have not seen a great example of people doing DAGs in the most challenging situations where you have hundreds of potential variables. People just come out with recommendations about, say, when variables should be measured in the course of things so that you have some hope of it not colliding with something. But I don't think we've seen enough examples. And I think right now it's a little bit too challenging, but we need to meet that challenge.
So the next question is related to the recommendation of horseshoe priors. Would you mind comparing them with spike and slab priors?
Yeah, I'm not up on the literature where those have been compared. My understanding from people that are doing this with real data with Bayes is there's benefits of the horseshoe prior. So the horseshoe prior, I don't know how to draw it, but it has you know, the Laplace distribution that's used in the lasso, it looks like this. And so, and then this point here is finite. So the density at 0 is finite. In the horseshoe prior, the density is infinite at 0. And so what happens with the horseshoe prior is you have a good probability of excluding variables, but then because it gives infinite density in here, it behaves better out here and still gets an area of 1. And so the lasso tends to do too much discounting of the very powerful variables, and horseshoe doesn't discount the powerful variables as much. I think in this way, horseshoe will work a little better than the spike and slab, but I don't have any experience with that.
Thank you very much. And you know, your talk was quite devastating towards feature selection. So, so when to perform feature selection? Because of course, this is a bit of killing data. So yeah, we are assuming that some of the variables are only have no relevance to the model. But other situations where feature selection is justified.
I can't think of many situations except if somebody is holding a gun to your head and saying, I can use 5 variables and no more. And so if you're needing to put something in the field and you can only measure 5 variables, you may need to work really hard to find out what are the 5 best variables. But feature selection is usually not the way to even do that. So what's usually a better way is you have collinearities. So you have variables that are hard to separate. And so if you do unsupervised learning, and one of the methods I like a lot is sparse principal components, which uses a lasso penalty for the coefficients or loadings in the principal components. But I really like variable clustering followed by regular principal components also. So when you do data reduction, which is also called unsupervised learning, you can actually respect the data. So you don't separate variables that are hard to separate. So where feature selection really fails is it tries to separate variables that are inseparable, and you find that you change one data point and it will select a different feature. So this is like collinearity problem. So if you do unsupervised learning, you'll prevent that problem. And then you'll have clusters of variables and you'll have fewer coefficients to estimate against the outcome. And then if you really want to do feature selection, you can select clusters of variables and add a lot more stability to the analysis.
Thank you. We have a question from John. So machine learning libraries actually are partially responsible for popularizing AUC, ROC curves, and so on, because they are very conventional and metrics in the field, and it's very easy to compute them. In R, you can easily plot ROC curve for every model you want. So is there a possibility to generalize your preferred metrics and plots to add to these frameworks? Are there such frameworks right now available?
So this is really, I'm going to give an answer that most people will hate. is one of the reasons that we have ROC curves and sensitivity and specificity is people have put it into software and made them too easy to get. This is not a benefit. This is a harm of software. So those things should not be in the software. Those are misleading measures that are completely incompatible with decision making. So the measures that I suggested are actually easier to program, easier to calculate, fast, and they generalize far more. So if you think about relative explained variation, what if you had a censored outcome variable? You know, how do you do ROC curves when you have censoring? It's really tricky. And so if you're doing relative explained variation, it's only using the linear predictors. And so the linear predictors don't care anything about censoring. They don't need to know about censoring. So if you calculated the variance of y hat, it doesn't matter whether y is binary, censored time to event, continuous. You have a general way to calculate relative explained variation. And so in this way, it has all of the advantages and very few of the disadvantages.
I think, you know, like Frank, that's the anti-ROC movement is growing. So it's not as complete heresy as it was like 10 years ago. But I think still many of our viewers will appreciate your novel viewpoint on that. So I want just to go back to the situation with only 5 variables, because someone on our chat is asking a question has a remark really based in the real life situations. So sometimes you are just asked to produce a simple model. People want simple models. For example, in a business setting, you often hear, or even in scientific one, as I can say from my own experience, people say, can't you reduce this problem just to a few features? We don't want to have a lot of features. Make it 5, make it 6. We need a very simple biomarker panel. We don't want to panel with 20 proteins or 100 proteins. Only 5 biomarkers, Michał, nothing more.
So this is going to irritate people. So let's suppose you have a master's degree in art history, or you have a PhD in solid state physics, and a job opens up 1,000 miles from your home. You're gonna take that job. If you're a data scientist and you're in a position where somebody tells you to do a bad job, you have so many options without going 1,000 miles away that you can find a different place to work. So if somebody tells you that they want a simple model and you are able to show with a simple bootstrap that there's no such thing as a simple model that's reliable, you need to do that. And so the biggest mistake that data analysts are making is assuming they have no power. And as soon as you act as if you have no power and you think that if you argued with the customer or you argued with the lead investigator that it's wrong to argue with them, you've already sacrificed your principles. And so you need to be working in a situation where you can actually have principles and adhere to the principles and not say yes just because you did not want to argue with someone.
I must admit, for a live-based question, we have a very live-based answer. Thank you for that. And very last question during this keynote, we will move after to the statistical misconceptions panel. But this is very last question by Sergey, and it's touching a very hot topic of the explainative machine learning. So what's your opinion of methods like LIME or SHAP values? What do you think about them?
So I'm not. How do you spell that? Because I don't know that I'm familiar with that.
It's the Shapley values. So this is a game theory thingy to explain the importance of the variable in the model. Let's say LIME has a bit different approach. It's basically fitting a small model to explain a small easy model to explain the large one.
Oh yeah, so that latter part is called model approximation. And it's also called preconditioning. I don't think we need to give it a third name. And so preconditioning and model approximation have been studied, not enough, but I think it is a good approach to have a gold standard model that's big, which might be a model that used ridge regression and not lasso. And so it's a big model, and then you approximate that model with smaller models. But the method that I referenced, the Bayesian method by the two authors, is a better approach than any of those in my view. But I think the bottom line is whatever method you're using, if you're afraid to calculate confidence intervals for it, you shouldn't use it. Because if you calculate confidence intervals on any of these measures, and if the confidence intervals show that you're doing an impossible task, you should find a different approach.
Frank, this is a great discussion. Unfortunately, I need to cut it. Let's switch to the statistical misconceptions panel. To all of our audience, thank you very much. We'll be at the statistical misconceptions panel in 1 minute. Thank you very much.
And so we switch to the different Zoom now.
Yes, sir.
See you shortly.
See you.